released or absorbed in the process, that is called calorimetry. So what is the core principle of this calorimetry? Actually, if you have this ice block and second one is the iron that have a 100 degrees Celsius temperature and ice have a 0 degrees Celsius temperature. If I mix these two in a bucket, so what will happen? Ice will gain energy and this iron will lose energy. This iron will lose energy and ice will gain energy. But whatever loss of energy will be there due to iron, same amount of energy will be gained due to ice. Means energy will remain conserved. So hot body always lose energy to reach at equilibrium and cold body always gain energy to reach at equilibrium. So it's a very basic concept of a calorimetry. Now, what is fundamental of that? Fundamental equation for that one is if Q amount of heat is supplied to any gas or any material, so M into S into delta T. So this is the definition of heat supply to the material. In this definition, Q is heat supplied, M is mass, S is called specific heat and delta T is temperature. We can rearrange this equation a bit. We can write S is equal to Q divided by M into delta T. Now in place of this M, if I write 1 kg and in place of delta T if I write 1 degree Celsius or else 1 Kelvin, so we can say that amount of heat supplied to increase temperature by 1 degree Celsius of 1 kg object. Means denominator if I write M is equal to 1 kg, delta T is equal to 1 kg, delta T is 1 degree Celsius, I can write S is equal to Q. So this is the definition of specific heat, amount of heat supplied to increase temperature of 1 kg body by 1 degree Celsius. And if you simplify this formula, we will get Q is equal to mc delta T. In place of S, we are using specific heat. C also we can use specific heat capacity C, or else we can use S. In case of low heat capacity means temperature rise will be quick. In case of high heat capacity, temperature rise will be slow. Now another concept is latent heat or hidden energy. So whenever any material changing from one state to another state, this ice is changing into water. In that case, what happened? The state is changing. State changing means initially ice means what? It's a solid, and again it convert into liquid. So if solid convert into liquid means state is changing. So whenever state is changing, when ice is melting, in that case what happen? That energy is used for melting of this ice. Means until complete ice will melt, temperature will remain 0 degrees Celsius only. Means at time of state change, whatever heat we supply, that will convert into energy that change in state, and we can write mathematically Q is equal to M into LF. In this case LF is called latent heat, hidden heat. So Q divided by M you can write, and we can define like that. If 1 kg material we have to change state, whatever heat required, that is LF. If I take 1 kg ice and if I convert 1 kg ice into water, so whatever amount of heat I have to give, that heat is called latent heat of a fusion. Why fusion? Because you're converting solid to liquid. Another heat, that is latent heat of vaporization. For example, if I take this one is water container and we are boiling this water. So right now this water is containing into vapor. So whenever water is containing into vapors, we can write Q is equal to M into LV. In this case also temperature of this water will remain constant, that will remain 100 degrees Celsius. So how to define LV? LV is equal to Q divided by M. Now amount of heat required to change 1 kg water into vapor steam, that is called LV, latent heat of vaporization. So this is latent heat of vaporization and this one is latent heat of fusion. In conclusion, if 1 kg water you have to convert into if 1 kg ice you have to convert into water, whatever heat is required, that is called latent heat of fusion. If 1 kg water you have to convert into steam, whatever heat is required, that is known as latent heat of a vaporization. This one is one ice block and we are making graph for this ice block. Means we are heating this ice block in a container, and when we are heating this ice block in a container, what will happen? First thing this ice will melt. But initially this ice is not at 0 degrees Celsius. Let's say this ice is at 12 degrees Celsius. So if ice is at 12 degrees Celsius, first what will happen? First this ice will reach from minus 12 degrees Celsius to 0 degrees Celsius. This is ice and this one also remain ice. But right now this ice is at 12 degrees Celsius and this ice will remain at. Alright. So now this is ice at 0 degrees Celsius. Now this ice reach from minus 12. Now at 0 degrees Celsius what will happen? This ice will melt and how much heat is supplied? MLV, MLF. In this case state will not change and temperature will not increase. So you can see that in y-axis temperature remain constant over here. Now this become water now, and water that again remain at 0 degrees Celsius. Now we keep on supplying the heat, what will happen? Water temperature will become 100 degrees Celsius. Again it still remain it water only, but temperature will remain 100 degrees Celsius. Now it reach at this point, and again if we keep on supplying the heat, then water will change into steam. So finally water will change into steam. So if this graph was happened from this point to this point, ice is changing from minus 12 to 0, still remain ice. As this point ice will melt, still remain at 0 degrees Celsius, but ice will melt and temperature remain constant. At this point now it become water and water temperature will increase to 100 degrees Celsius, and at 100 degrees Celsius water will convert into steam, and when it will convert into steam, again if you are supplying heat, temperature. Alright, so in this question it's given a copper sphere 10 degrees Celsius is dropped from height 4 km, is heated due to air resistance. Okay, let's assume that all kinetic energy is used to increase temperature, right? If the specific heat of copper is given this much, find the final temperature of the sphere. Now we know if something is falling from height h, so we can write 2gh is equal to velocity. So if I substitute value 2 into g in place of g, that is 10, or s is equal to 4000, we can calculate v from this one. Now this whole energy will convert into heat energy, so we can write ms into delta t. Now m and m get cancelled and we know v square by 2, that is equal to s into delta t. Delta T they are asking for and specific heat is given to you. It means V square, that is 2 into 10 into 4000 divided by 2 and divided by 384, that will be delta T. That's how we can calculate temperature of this one. Now the temperature of equal mass of three liquid A, B and C, 15, 20 and 30. So we'll draw these three liquid. First one is A, second is B and third one is C. So this A, this is B, this is C. This one is 15 degree, this one is 20 degree and this one is 30 degree. Right. Now when A and B are mixed, equilibrium temperature is 18. When B and C are mixed, equilibrium temperature is 22. What will be equilibrium temperature when liquid A and C are mixed? So what they are saying, when A and B are mixed, temperature equilibrium that become 18. Means what I can write, heat given by B, heat loss by B, because B temperature is 20 degrees Celsius and A temperature is 15. It means B will lose heat and A will get heat. Now heat loss by B is equal to heat gain by A. So heat loss by B will be equal to mass of B into specific heat of B into delta T. Delta T will be how much? 20 minus 18. And heat gain by A, mass of A into specific heat of A, and heat gain by A, that will be 18 minus 15. From this one we can write 2SB is equal to SA and rest of thing get cancelled. Alright. Now we are mixing B and C. So this is B and this one is C, and B temperature is 20 degrees Celsius, C temperature is 30 degrees Celsius. This is B and this one is C. Now when we are mixing these two, equilibrium temperature become 22 degrees Celsius. Means C will lose heat and B will gain heat. So what is heat loss due to C? Mass of C into specific heat of C into 30 minus 22. And what will be heat gain by B? Mass of B into specific heat of B into 22 minus 20. Now if I solve these two, I will get SB is equal to 4 times of SC. Now last case between A and C. This is A and this one is C. So last case is between A and C, and A temperature is 15 and C temperature is 30. So obviously C will lose heat and A will gain heat. And equilibrium temperature they are asking. Let's say equilibrium temperature is X. So what I can write, heat loss by C is equal to heat gain by A. So what will be heat loss by C? M into SC into 30 minus X is equal to heat gain by A, M into, that is SA into X minus 15. Now we know SC and we know SA. SC and SA we can write in terms of SC, we can write SB by 4 and SA we can write 2SB. So in place of SC I will write SB divided by 4 into 30 minus X, that should be equal to M into SA, we can write 2SB into X minus 15. Now SB get cancelled and we solve this equation, we will get X is equal to 19.09 degrees Celsius. We have a 2 kg block of copper 100 degrees Celsius and put in ice container with have a 0.7 kg ice at 0 degrees Celsius. Find equilibrium temperature and final composition of mixture given that specific heat of copper is this and that of water is this one and that latent heat of fusion is this one, 3.36 into 10 raised to 5. Now when we mix copper to ice, so copper will give energy, means heat given by the copper. So that heat given by copper is equal to mass of copper specific heat of copper into delta T, and copper is reaching from 100 to 0 for equilibrium. So what is mass of copper? Mass of copper is given 2 kg. So if I find out, if I calculate this one, 378 into 100. If I calculate this one, that will be 7.56 into 10 raised to 4 joule. This much heat copper will give. Now, what is required heat to melt complete ice? To melt complete ice, Q is equal to M into LF, and M into LF, and M is how much? To melt complete ice, M into LF, and M is how much? Mass of that ice is how much? 0.75. And what's the specific heat of this one? Latent heat basically 3.36 into 10 raised to 5. If we calculate this one will be 25.2 into 10 raised to minus 4. So this is heat given and this is heat required. Now you can see that heat given is less and heat required is more. It means complete ice will not melt. It means in container ice will be left, and if ice will be left, in that case temperature will remain 0 degrees Celsius. Why? Because some ice melted and some ice already remain there. Now, how much ice melted? So this much heat is needed to melt ice. So only this much ice will be melted, and what ice will be remaining? Ice will be remaining, that is 25 into 2 into 10 raised to minus 4. This much required heat, but how much heat it got? 27.56 into 10 raised to 4, that is equal to M into LF. And if I solve this one, so I'll get LF is equal to 17.64 into 10 raised to 4 divided by 3.36 into 10 raised to 5, and that will be equal to 5.25 kg. Means in container there will be 2 kg copper plus 0.527 kg ice plus total ice was 0.75. If we subtract 0.75 minus 0.527, 525. So what we'll get if we subtract that one? So we will get 0.225. So 0.225 water. So in final mixture, what will be there? Copper 2 kg, ice 0.525 kg, and water 0.225 kg. Mixing 0.5 kg ice at 0 degrees Celsius with 2 kg water at 30 degrees Celsius. Given that latent heat of ice is this one and specific heat of water is this. Now what happened? How much heat we get when we are mixing 2 kg water at 0 degrees Celsius? So first this is 2 kg water and we are bringing it at 0 degrees Celsius. Means how much heat is released? Q1 is equal to M into S into delta T. And what's the mass of that one? 2 kg. And specific heat of this one is 4200, and temperature difference is 30 minus 0, so that will be 30 only. That will be 2.52 into 10 raised to 5 joule. Now this much heat ice will give, so this much heat water will give. How much heat is required to melt complete ice? That we'll see, that M into LF. And what's the value of M? Mass of ice is 0.5, and what's the LF? 3.36 into 10 raised to 5. Now if I calculate this one, it will be 1.68 into 10 raised to 5 joule. Means what is heat given by water? This much, and heat required to melt ice this much. So now complete ice will be melted, as because heat given by the water is this and heat required to ice is this one. So heat required basically it's less. This is less than this one. So in that case complete ice will melt. Now how much energy will be left if complete ice will melt? Energy will be left, that is 2.52 into 10 raised to 5 minus 1.68 into 10 raised to 5 joule. So if we calculate this one, 8.4 into 10 raised to 4 joule energy will be left. Energy will be left. Now this much energy is required to increase temperature of this whole thing, ice, water, plus that ice that also become water. So that ice also become water means what is total water now? 2.5 kg. So what I'll write, m into s into delta t is equal to this much heat is required to increase temperature of whole thing. Whole thing means that ice also become water now. So this one I'll write 2.5 and specific heat 4200 and delta T, that is T minus 0, that is 8.4 into 10 raised to 4 joule. If I solve this whole thing, I will get temperature is 8 degrees Celsius.